Hello everyone and welcome to Android Heroes Live. Today I'm here in Turin in the Synesthesia studio and I'm very excited because we have with us an awesome guest that is going to talk about one of my favorite topics, which is graphics. I am more of an amateur of the topic than an actual professional, but we have the professional here. And as the Netflix show My Next Guest Needs No Introduction, this is one such case, but I'm gonna try anyway. My next guest is, sorry, small difficulties. My next guest is Romain Guy, Romain from Google. Hi Romain, welcome.
Hey, how are you doing?
I'm doing all right, how are you doing?
Good. It's exciting to give a talk. We didn't have many opportunities over the past a year and a half, so it's always fun to be able to talk to the community.
Yeah, and hopefully next time we'll all be in Turin in person.
I do hope so. Yes.
I can tell you it's worth for the food, if anything else.
Completely agree.
So for those who don't know, and I don't know if that's a thing, Roman works at Google and he has been a pillar of the Android UI toolkit and you have dabbled in robotics as well, I think, over time.
Yeah, a little bit. That was just a detour.
Related. And now you are working on Compose, right?
Well, I am not working on Compose. I manage the team that does the actual work. So everything you love about Compose, you have to thank all the great engineers on the team, not me.
Well, we have to thank you for letting them work on it, I guess.
I hope I'm being useful. Yes.
Okay, so what are you talking about today specifically?
Yeah, so today it's a talk that Chet and I have been wanting to give for a long time, which is basically a tour of the world of graphics for Android developers. But when we started looking into it, we realized that it's a very broad topic, and it would take probably 10 hours to go through all of it, and even then. So this is just the first installment. It's just about the foundation. So it's about what is a pixel, what is a color, what are bitmaps, what are vectors. And hopefully soon we'll have the sequel where we're gonna go into more details into all of those things.
So this is more like the philosophy of graphics, if you will.
Yeah, a little bit. I mean, the idea is to go back to the fundamentals. Like we're huge believers in understanding the how things work at a fundamental level, so that you can be like the best engineer you can be at the high level. And also, frankly, I always find it interesting to learn about this low level stuff. So it's not going to be too technical, but hopefully you will learn a few things.
I am looking forward to it. So I'm leaving you the floor and thank you again for being with us today.
All right, thank you. All right, let's get started. So yeah, this is a talk that Chet and I came up with. So you see his name on the slides. Unfortunately, he's not giving the talk today with me. And like I said, we won't be able, or I won't be able to go through all of graphics. So we're going to focus on 2D graphics, and we're going to focus on some of 2D graphics. So we call it kind of like mostly 2D graphics for developers, because there's not much that's Android specific either in this talk. All right. So before we get started, we're going to talk about pixels. We're all familiar with them. So this is a white screen. And obviously, if you were to look deeper, like at your actual display, you would not see, a uniform white. Instead, you would see like a grid of little things that we call picture elements or pixels. But if you were to zoom in even closer to those pixels, you will see this. You will see 3 red lights, R, G, and B. So every individual pixel is made of sub-elements. It's kind of like when we discovered the atom, and then we discovered that those things are made of like smaller things. So same idea here. We often talk about pixels when we write code, but they're not the most fundamental element that we're actually dealing with. And obviously, the rest of your screen is made of those pixels. So the question is, like, we have this, bright white image on screen, and yet when we zoom in, we see like those smaller, like totally non-white things that are shining at us. So how does it work? So the key here is something called additive color mixing. And it's not just about the color mixing, it's also about the fact that we sit at a distance from our display. So it's this combination of mixing and distance that makes it work. So on the previous slide, we were effectively looking at the screen really, really close. You can't really anymore like get so close to a screen that you will see those RGB lights, but you can use macro lenses or microscope to see them, and I'll show you photos of that in a little bit. But realistically, when you sit at a normal working distance from your screen, the additive mixing is going to take effect. And it's a mixing form, but it's also about the resolution power of our eyes. So our eyes can only distinguish details of a certain size at a certain distance. And that's why high density displays work so well nowadays, because we made the pixels or the subpixels so small that even when we stand really close to a screen, we can't tell the difference anymore. If you go back, 15 years and you look at some of the first smartphones, you can totally see those subpixels. You can see the fringing on the anti-aliasing. So one way to think about it is like, you get the red light of the pixel shining at you, then you get the blue light and the green light, and they combine together to do white. Again, this is a bit misleading because those are not projectors. So it's more about like how our eyes like resolve those details and combine them. But if we are to look at it from, so we have this red light. Because of this, again, resolution power and the distance, we're going to mix it with a green light. It's going to give us yellow. And then when we mix it in our brain with the blue light, we get white. And that's where like we're going to take a little detour and we're going to talk a bit about art. There was a thing that Chet really cared about. So this painting is called A Sunday, Un Dimanche à la Grande Jatte by Georges Seurat. And Seurat perfected a technique called pointillism. So the idea was, instead of mixing different paints to achieve the desired color mix, instead he would use more primary colors. He would use like individual colors that were readily available, and he would effectively paint the equivalent of pixels. And again, here, like with the distance and the resolution power of our eyes, we would like create those extra colors without having to mix the paint. And the reason why he did that was to create a brighter painting, because he could use those more primary colors and also avoiding the mixing, and we'll take a look at why it works in a minute, really helps like creating those more vibrant paintings. So if we look at another example, so this is Evening Calm by Paul Signac. If we look closely at the painting, oops, this is what it looks like. You can see like those individual touches of paint. They're really like those pixels. And again, when you stand far away from the painting, our brain will automatically do this mixing. So if you look on the right, for instance, there's this blue chunk that will help like change the color from far away. So we've already talked about two types of mixing of color. There's the additive mixing, that's what we have in our displays, and then there's the subtractive mixing, that's what we use with paints, and this is probably the one that you learned in school. And I remember when I started doing graphics programming, I've always had those confusing conversations with friends and family because, when they would ask me how to do yellow, I would say, well, you mix red and green, and they were really confused because that's not how you do it with paint, right? Like yellow is a primary when you use paint. So additive color, obviously it's in the name, it adds color information. So that's what you get when you use colored lights. And when you use bright paint colors, they mostly reflect light. So when the light gets reflected of the paint, like those bits of paint that are close together, like we just saw in those paintings, they add up together when they reach our eyes and we get the result, the desired result. And subtractive color obviously subtracts color information. This is also, we've already seen it, you do red and green, you get yellow, you add blue and you get white, and you can see the complementary colors, the cyan, the magenta, and the yellow here on screen. With subtractive color, so that's what you get when you mix oil paints, for instance, or when you use colored light filters. If you have a bright light, a white light, and you put a colored gel in front of it, let's say a red gel, everything you're going to see is going to be red, and it's because that gel will remove all color information except the red wavelength from the light. And when you subtractive color, so you use those different primaries. So you have magenta, you can mix it with yellow, you get red, you have cyan, and when you mix it with the other two, you get black. Or more realistically, whenever you mix paints, like I don't know about you, but that's what always happens to me as well. I get a brown. I never get really black. So what happens in the paint itself? So this is a simplified view of what's happening, but basically you have light that comes in, right? That's going to hit the paint layer, and some of that light will bounce off. It will be reflected. So that will depend on the nature of the paint. Some paints are glossy, some paints are more matte, but always some amount of light will get reflected. Then the rest of the light will penetrate the paint and will get scattered, right? Like you can imagine that the inside of the paint is made of like tiny like mirrors that will send the directions. And during that process, some of the light will get absorbed completely. You will lose the energy that's carried by the light inside the paint itself. Then eventually, some of the light will come back out. And what comes out, let's say you have a red paint, is all the incoming light where you subtracted everything that's not red. Now, what's interesting is what comes out. You can see it here. Again, so we did the subtractive mixing, but when it comes out, we're gonna get back to the additive mixing mode again, because it's light that's coming out. So that's where, like, if you have if this was red and if this was green, our eyes would like mix those two colors together in the additive way. So here's another example. Like that's a painting that actually hangs in Chet's house, and this painting always freaked me out. Not sure why. This is a crop of the painting, but it's interesting because you can see that white is the only color in this example where that approach is the kind of brightness you get from a display, and even then it's not that bright, and it's because even with the best paint, some of the light will get absorbed, so you will get dimmer than the environment, and the darker colors are much richer. What's also interesting, if you look at the black paint, you can see those specks of white. That's light reflected off the paint. So even though it appears black because it absorbs like most of the incoming light, some of it will reflect before it gets even a chance to be absorbed, and that's why you get those reflections on the paint. All right. But we're interested in computers and phones, and this is not how they work. This is how they work. So this is a macro photo that I took of my 4K TV in my living room, and you can see the image here. Actually, it's pretty cool. You can even see like the electronics between the pixels themselves, and you can see that each pixel a bit of green, a bit of blue, a bit of red. And in this particular case, there's also a white element. So some displays do this to be able to reach enough brightness, but it's not necessary. It's often about like power savings and stuff like that. It's not necessary to the color information. Now, what's interesting is that if you look at the blue subpixels, they are bigger. They're actually twice as big as the red ones and the green ones. And that's because our eyes are less sensitive to blue light. Actually, we see very, very poorly in blue light. So we need like more blue to be able to perceive it at the same intensity as the rest. And this is another macro picture. This is a picture of my Pixel 4. This is also a macro shot. So I was showing a white image, and you can see that it's actually a bunch of subpixels. What's interesting here is that, again, the blue subpixels are much bigger. The red pixels are not quite as big as the blue pixel, but they're bigger than the green pixels. And if you were to count them, you would see there's twice as many green pixels or subpixels. And it's because our eyes are the most sensitive to green light. This is how we perceive pretty much sharpness and motion. So another detour really quickly. So I already said that our eyes are more sensitive to blue, and I want to explain why. So light, or at least what we call color or what we call light, is part of the radio spectrum. So you can think of our eyes, oddly enough, as radio receptors, right? They're really like little antennas, and we perceive radio waves. We just happen to perceive only some of the radio waves, so that's the color spectrum. The radio spectrum has a lot more. There's infrareds, there's X-rays, there's gamma rays, but we don't see those. Now, our eyes are made of something called cones. There's also rods, but we have three types of cones. They're like just tiny receptors at the back of our eyes. And we have three types of cones that we call short, medium, and long. And if we were to map their sensitivity over the colored spectrum, this is what it looks like. So you can see that we have one type of cones that can perceive blue, but our other types of cones can perceive the non-blue part of the spectrum a lot more. So it's wider and they also overlap. This is why we see blue a lot less well than we see the rest. And you can see that around green, that's when we have the most overlap between two types of our cones, and that's why we're so sensitive to green compared to the other colors. All right, so we talked about a lot of physical details, but why do we care? Why do we care about those red light and blue colors? And that's because, you know, our pixels are RGB, and we use RGB values directly in our apps. This is something that you're familiar with. So here's an example of how you would draw the background of a view. You could draw a color on your canvas. You have here I pass the value 255, 0 to 55. It's a mix of red and blue, so that they will produce magenta. And also, you know, it's interesting, but it's really because to be able to use those APIs efficiently, it's good to understand how things work in real life. But now if we take a step back, so I just said, like, you know, we mixed when we got magenta, but you could ask yourself, like, what is the red we're using? Is there one red in nature, right? Or are there multiple and we just decided to pick one? So we're going to take another step back and just think about what is a color. So a color fundamentally is a tuple of numbers or series of numbers. Most of the time it's a triplet like R, G, and B. And the color model, and that color model has a color space. So we're going to look at what do things mean. A color model is effectively the number of values, the range of values that you can use to describe a color. So obviously the most common one is RGB. There are other ones. For instance, there's the one called lab. CMYK is used for printing. So this is the subtractive model. So that's cyan, magenta, yellow, and black. The K stands for black. And there are many others like HSV, HSL. You know, there are as many as you want. You could even create your own. So once you have a color model, you can create values, right, in that model to represent a color. So here we have RGB, and I put several examples of how we can encode the values. It almost doesn't matter. So we have the hexadecimal model. We have the model using 0 to 255 because it fits in bytes as integers, or you can use floating points values. The point is that we just need a way to have numbers. But obviously that's not enough. So to understand why that's not enough, we need to look at the range of colors that we can perceive with our eyes. So this is something called a chromaticity diagram. It's presentation. It's actually a 3D diagram, and I will show you a short video in a little bit. But this gives you an idea of like everything we can see. And everything that's outside of this diagram are imaginary colors, or they're effectively the type of radio waves that we cannot perceive. Like we don't have the hardware in our eyes to be able to see those colors. So no matter what we do, all the colors that we want will be somewhere in that odd shape. And you can see already that that shape is not very, it's pretty difficult to use when you only have RGB values. So remember, we said that RGB, we use the additive model. So we start with like 3 types of lights, red, green, and blue, and we're going to mix them. So if you were to do a graphical representation of this idea of mixing primaries, you would end up with a triangle, right? So this would be our pure blue, our pure red, and our pure green. And if I mix green and blue, I will be somewhere along this line. Then if I add some red, I will go this way. So with the RGB model, all you can specify, even with an infinite precision, will fall somewhere inside a triangle. And that is our pure blue, what is our pure red, what is our pure green. And we can pick any that we want within the colors, within the visible spectrum. And that's a color space. That defines, okay, what is red, what is blue, what is green. And that means we need to pick one. So a common one is called Srgb, and here I'm showing you the 3D version of Srgb, and you can see the triangle that we just looked at here at the bottom. And you can see that the higher we go in the brightness, the fewer colors there is, the volume like shrinks. And this is because our eyes are way more sensitive to the dark, hues. So we have much more precision in our eyes in the dark. So you can see that the volume is much bigger. And the brighter things get, the less probably an evolutionary advantage, being able to see better in the dark, or like, being able to resolve details like, I don't know, when there's a predator about to eat you or something like that. Anyway, so that's how we represent colors. So I mentioned there are multiple color spaces. Srgb is the most common one. So you can see here, Srgb is this blue triangle on this diagram. There are other ones. So here I put Adobe Rgb. It's commonly used in photos. So you can see already that if we say that we have a color that's 0 to 2550 in Srgb, it will be green. So it will be a green right here. But the same value in Adobe Rgb will be a different green. And that's why it's very important to always know what color space you're using. I've also added another color space called Profoto Rgb. This one is used also when you do photography, but it's not used to display the final image. It's a working color space because you can see it extends beyond the visible spectrum. So it contains color. All right, so now we know what is a color and why it's important for pixels. So where are pixels used? Obviously, they're used everywhere in your application, right? That's how we display the UI to the user. But ideally, you will never use them directly, right? They're the building blocks of all graphics. And you can address those pixels individually. And we even have APIs for that. For instance, you can do canvas.draw point to draw a single point. On a bitmap, you can call get pixel or set pixel. But really, like, it's a tedious way of doing this, and you should use other primitives, higher level primitives, to do all your rendering. And you do. There's one exception. When you program the GPU, you use something called fragment shaders. They're not really pixels, but they're almost pixels. So unless you do like GPU rendering, like, you don't really have to worry about it, but that's the way GPUs work. You effectively write a program that tells the GPU what is the exact color of a given pixel. Like, it's a different way of working. So instead, like I said, we use high-level primitives. So the first one we're going to look at is the bitmap, or image, or pictures. And obviously, confusingly enough, on Android, we have something called a picture, and it's not really a bitmap. It's more a list of commands for the canvas. All right, so most of the screen content that you see is made of bitmaps, or at least used to be made of bitmaps. So, photos, images, but even the UI objects, right? Like all the buttons and things like that, until fairly recently on Android, were made of bitmaps. And even text, and we're going to look at how it works, but text is also made of a bunch of little bitmaps. And bitmaps are also confusing because there are so many ways of manipulating bitmaps, and there are so many file formats. Just to name a few, there's JPEG and GIF and WebP and PNG and TIFF, and every year we keep adding new ones. Android 12, I already forgot the name, AVIF, we just added yet another file format. So why do we need so many formats? Like, why can't we just have those RGB values and put them in a file and be done with it? So yeah, we could do that, but we're gonna see that it's not the best way of doing it. So to illustrate our what I'm saying, we're gonna take a very simple bitmap. It's a 100 by 100 bitmap made only of white. And so to represent white, we're gonna store each RGB value as a byte. So if we encode it as a BMP, we're going to end up with a file that's 40 kilobytes. It's 40 kilobytes because even though we need only 3 values, we're going to store 4 over 32 bits because it's just more convenient. And that's something we often do in graphics. When you use RGB, we always add another byte because it helps with alignment and makes algorithms a lot simpler. So your BMP is going to be 40 kilobytes. And incidentally, if you do 100 times 100 times 4 bytes, that's exactly 40 kilobytes. So BMP is basically the raw data of your image stored on disk. Now, if we encode this as a JPEG, it's going to be only 4 kilobytes. As a GIF, it's going to be 156 bytes. So it's very efficient. And a PNG is going to be one kilobyte. Now, let's look at another image that will force those file formats to behave differently. So this is a gradient. Same size of the image, so the BMP still has the same size on disk because it doesn't care, just a raw version of the file. And now our JPEG is a little bigger, it's 6 kilobytes. The GIF is way bigger than it used to be. It went from 150 bytes to 3 kilobytes, and PNG is 8 kilobytes. So already you're starting to see like that some formats might be better at encoding different types of information. So PNG in particular is very sensitive to changes in color from one pixel to the other. And it's going to be terrible for things like photos, like this one. So this is a much bigger picture. It's 6,000 by 4,000. So as a BMP, it's 96 megabytes. That's the raw values again. The JPEG is about 5 megs. GIF is way bigger than it used to be. It's twice the size of JPEG now. And PNG is even larger still. And again, that's a great example where PNG is terrible because it encodes effectively deltas from one pixel to the other vertically and horizontally. And when the values of the pixels change all the time, this is the worst that you can do for PNG. So not only do we have a difference in disk size, but we also have a difference in quality. It might be difficult to see on screen, unfortunately, but our GIF here is bigger than JPEG the way it only encodes a palette of colors, so 256 colors. There are a lot of colors it cannot encode. This is actually a good use case for GIF because there's not much variation. But if you look at the sky, hopefully you can see some bending, like you can see bands of blue, whereas the JPEG has this very smooth gradient. And it's because GIF just cannot do. Another example, this is much more visible. So that gradient, again, you can see that GIF has this horrible bending, and we can zoom in on it. And you can see like it's not even straight. We can see that little staircase effect. So you have to pick the format that's best for your content. And beyond that, like the formats also offer different levels of convenience. So in JPEG, you can choose how much you want to spend on disk versus the quality of the image, but you cannot use translucency or alpha. GIF offers 1 bit of transparency, so a pixel can be on or off, but you cannot have anti-aliasing, for instance. You're limited to 256 colors. There are actually ways to go around this limitation, but it's not the point of this talk. PNG is more flexible. You have full translucency, but it's a lossless format, so it's always going to be slightly bigger, especially for photos. Webp is interesting because you can choose to be lossy or lossless. And it supports various features like animations, alpha, and so on. And newer formats like AVIF can do HDR. They can encode over 10 or 12 bit of color depth. So they can have even more precision and more color information. And BMP, like we saw, is just the raw values. So choose your format carefully based on what you need. Lossiness, detail, color information. Do you need translucency? What size can you afford? And whether or not you need animations. And the reason I talk about all this is because the file size on disk is very different from the size in memory. And it's surprising, at least surprising, but taking a step back, like it's because I live in that world, but it's the most common confusion we see about bitmaps. So not this month exactly, but I remember like working with a team at Google that was using our 3D renderer, and they were confused because when they were loading an object with textures, they would see the memory usage spike up. And so I asked them like, okay, so what are your textures? And they're like, oh, they're really small. They're like, 4 kilobytes PNGs. I'm like, okay. And I looked at the PNG files. Yeah, they were 4 kilobytes, but they were like 4,000 by 4,000 gray PNGs with a single color. So yes, they were 4 kilobytes on disk, but once we expand them in RAM, they were using something like 68 megs of RAM. So huge difference. So let's take an example. So we have our 100 by 100 JPEG. It's 4 kilobytes. Then we can use the bitmap factory to decode it. And then on bitmap, we have this getter, so you can call allocation byte count. It will tell you the exact amount of bytes that the bitmap is currently using. So when we do this with this small JPEG, we get 40 kilobyte as the result. So that means there's a 10-to-1 compression ratio between the space in memory and the space on disk. Now, if we use a bigger JPEG, like 2000 by 2000, and we do the same thing, we're going to get a different number. So it's 16 megabytes, and that gives us a much better compression ratio, so 238-to-1. So again, like seeing a small file doesn't mean it's not going to be huge in memory. So bitmaps are big. What should you do? Something you don't want to hear as a Kotlin or a Java developer, manage your memory, right? Only load the size of bitmap you need. And that's important because on Android, it's also a mistake I see made very often, especially from developers who have not the early days of Android, and I can't blame them. So we have this drawable directory. So if you say drawable -xx HDPI, it's for certain density. But if you say drawable without any qualifier, it actually means drawable-m DPI. So that was the density of the first Android display. Uh, and displays are now about 4 times as dense compared to 15 years ago. So if you put a file in the drawable/folder and you load it on a modern device, we're going to automatically scale the bitmap to 4 times its size on each axis. So it's going to be 16 times larger in memory. So I've seen people trying to load high-resolution images, and they put them in that folder, and they run out of memory trying to load that only file. And that's because the system is trying to upscale it on their behalf. So what you should do is put the bitmaps in the right density folder, or if you know what you're doing, there's a lesser known qualifier called no DPI. So you can say drawable-no DPI, and images that you put there are guaranteed to never be scaled by the system, right? When you decode them, you will see what the file contains and nothing else. So only keep the bitmaps you need and use a good bitmap cache, reduce the bitmap memory. The best way to do that, honestly, is to use a library, right? There's a number of choices, and I'm sure you're already using some of them, like Glide, Picasso, Coil. They're really well integrated with both the existing UI toolkit and the upcoming Jetpack Compose. That's the right way to handle your bitmaps. Drawing bitmaps, there are several ways. You can draw them directly on canvas with the draw bitmap method. Most of the time, you're going to go through a bitmap drawable. Those can be attached as the background of a view. They can be used in a number of situations. And they're great, and that's probably the right way to do this. It just makes it a little more complicated sometimes to know like where the bitmap is coming from and how big it is. Or you can use an image view directly, but internally, all it does is use a drawable. All right, so I mentioned text already, and I said that text is drawn as bitmaps. We're going to see text inside fonts to a long time ago, in the 80s and early 90s, were actually bitmaps. They're not anymore. Now they're vectors, and it makes the font size smaller. It also allows us to draw text at really large sizes and small sizes and get really high quality. But internally, it's very expensive to do it this way. So text is actually converted into bitmaps in what we call an atlas. And then those bitmaps are copied onto the screen to create the text. It's way faster in many ways. So we're going to take an example. Let's say we want to draw the word cool on screen. So inside the font, we're going to go fetch the letter C. We're going to make it go through a special renderer. So we use FreeType. FreeType is a very well-known open source library that takes the vector information from the fonts and gives you either that information directly or gives you a bitmap representation for given font size and font weight and so on. So we're going to ask FreeType for a bitmap, and we're going to put our glyph cache. So we're going to have a tiny bitmap, or actually, you can think of the glyph cache as a giant bitmap, and we're going to have sub-region of that bitmap where we know we have specific letters. So that's what we're going to do. Then we need the letter O, so we're going to do the same thing. We put it in the cache. Then we need O again, but we already have O in the cache, so we don't need to put it a second time. Then we find our L, and we put it in the cache. And then when we need to draw the text on screen, we're just going to go fetch that information from the bitmap cache, from the glyph cache. There are other ways of doing this, especially on the GPU, but this is, I believe, still how it works on Android today. Again, because it's very simple, very efficient. It becomes a bit complicated when you use a lot of emojis, or when you use languages like Chinese that have many characters, like many different glyphs. So the management of that cache is very complicated, but in the end, we're just drawing like small bitmaps on screen. All right, so bitmaps are great for when you scale them up or down, right? Like you have thumbnails and you're trying to scale it up, or the other way around. And there are two types of filtering that we offer on Android. There are other ways of filtering bitmaps that I'm not going to discuss here today. Like it's basically signal theory. It's a whole field. It's very interesting, but it gets complicated very fast. But you have to be careful when you scale bitmaps. So here's an example of a bitmap with red, blue, green, and black. And if we don't sample it with the default filter, it's what's called the point filtering, or just pixel filtering. We're going to we're gonna take the pixels at the destination and find the closest pixel in the source image. And you can see in this example that we're just losing a ton of information, right? Like blue and black have completely disappeared. Now, if we use bilinear filtering, what we're going to do instead is look at the pixels around the pixel we need and come up with the average. So that's going to give us a weird result here that's also not what we want. But on average, for most images, it's going to give us much better results. And we're not losing as much information because we are doing an average of what's around it, right? Here, we are dropping the information completely. With bilinear filtering, we're keeping some of it in the form of an average. Now, if you have geometry inside a bitmap, scaling it is a terrible idea. So here's a simple bitmap that contains a straight line. And if we scale it up using point sampling, you're going to get those results, right? Like it's still our line, but it looks pretty bad, right? Like it looks like a staircase, not like a line. Now we can switch the filtering to use bilinear filtering, but we're just going to get this blurry mess instead. And it's not, and you can even see like inside, the line, you can see this like star shape. You're actually seeing the shape of the bilinear pattern. So it has its drawbacks as well. Not great. Downscaling can also be weird. So here's a pretty bad case. So we have a checkerboard pattern. If we downsample it using point filtering, you're gonna get these different results, right? Like you're gonna lose the pattern, or you're gonna create a pattern that's bigger. It doesn't look good. You can try to use filtering, but we're also gonna get like really bizarre results. And this average of black and white pixels are just gonna give us gray, which is not at all what you're seeing on screen, unless like you squint really hard and step far away from the monitor. That's not what you're gonna see. So scaling bitmaps works-ish, but it's by no means like a perfect solution. So you have to be very careful when you do that. And I'm mentioning that because some of our UI geometry must scale, right? Like I mentioned, when we are using background drawables, let's say for a button, depending on the size of the text that's inside, we may need to like change the size of the button. And if we were to just scale the bitmap without thinking of it properly, we would get like this mess, right? Like as the button grows, like we scale the corners and we scale the strokes, and it looks disgusting. And that's why on Android, we have this thing called 9-patch, which is actually, more specifically, it's an end patch. So what it does is that some parts of the bitmap will scale and some parts will be copied as is. So the way it works is that your 9-patch, you define regions of scaling. So in this example, everything in green will be preserved exactly as it is, and the pink region will be stretched, will be scaled. So when we grow the button, we can stretch this really safe region, and actually it's a little wrong because you can see there's a bit of anti-aliasing left here that's going to be scaled, but our corners are going to stay the same, right? So it's going to work really well. But 9-patch is a workaround, and what we would need is a fix instead of a workaround, and what you really want is actual geometry, and that's why nowadays, hopefully, using vectors for pretty much anything, right? Vector drawables. The nice thing about vectors is that they are effectively canvas commands. They're just instruction. They're not like pixel information like bitmaps. So we can render them at any resolution and make sure that they will look good. So mostly vectors, when you think vectors, you can think draw path on canvas. That's what it is. So it's an example of drawing a line. You can also draw some common primitives like rounded rects, or you can use draw path, and you can do like any shape that you want. What's interesting too is that internally in the rendering system, when you draw a rounded rect or a circle, we're likely to actually ask the system to draw a path. That way we have a single code path to render the path instead of having code that's specific to different shapes. For instance, a circle can be approximated using 8 curves inside a path, and the approximation is good enough that we won't see the difference with pixels. So if we take a look at vector drawable, like I said, it's a declarative format, contains a limited set of the canvas commands. So you can have transforms and gradients and alpha, like here. So for instance, when we set the pivot and the rotation, it's actually going to call set matrix on the canvas. The fill color is going to set a style. And then the path data is going to contain information on how to create a path object. So The M means move to 370, that's a coordinate. Then we have a L, that's a line to. And then when there's no letter, we just repeat the last comment. So it's just a bunch of lines in this example. So very efficient format on disk, and you get perfect representation on screen. Of course, it makes it very difficult. You would not represent a photo that way because you would need a lot of tiny paths. It would be very inefficient. There are other formats you can use. You can use Lottie, which hopefully you have used before. So it lets you export complex vector animations from After Effects. It's much richer than Vector Drawable. There's also SVG, but we don't really use that one. Lottie is, I think, a much better one. And last thing I want to show you is how we render paths. So, those vectors, those curves, like they're a bit, there's a bit of mystery going on. So here I took a simple curve that I drew in, I think, Keynote. And if I use the path or curve in any drawing program like Photoshop or Keynote or whatever else, you've seen those handles, right? Like you can move those handles and you can change what the curve looks like. So that's great for the user, but those curves are actually very important to the rendering process. So I'm going to describe the rendering process. Like this is the common way to render path on the CPU. So we're going to take those two handles and we're going to find the center point on each one of those lines. Then we're going to connect the two handles and we're going to find the middle point. So we get those pink lines. Then we're going to find the middle point of those pink lines and we're going to create another line, the green line. And the middle point of that is guaranteed mathematically to be on our original curve. It's a cubic curve. And incidentally, what we've just done is we found a way to split our original curve into two new curves. And even better than that, not only have we found a subcurve, but we've also found the handles, there's one here and one here, of the new curve. So now we can focus on that new curve. And we can repeat this process. We can re-subdivide it. It's crap, what's the word? Not iterative process. My brain's broken. To repeat and over again until we deem that the curve is small enough. And how do we decide that? So we look at something called the flatness of the curve. So you can imagine the flatness as this metric, right? We can take the first point on the curve and the last point on the curve. We can find the maximum point of the curve, and we can look at what is that distance. And when that distance is less than, let's say, half or a quarter of a pixel, well, that means that the height of the curve is less than a pixel. So we cannot render that curve anymore. It's actually a line. So what we're going to do is we're going to replace that curve with a line. So we're going to take the curves, split them up until we split them enough that we find a bunch of lines. And drawing lines, we know how to do that. It's super easy. So here, that's what we've done. We took the curve, we subdivided into a bunch of lines, and you can see the pixels, at that resolution, it looks like this. What's really neat is that we can do this at other resolutions. So here at a lower resolution, and will still look great, right? Like this is not like a bitmap. It's not going to look gross. We're not going to lose information. We're going to compute exactly the coverage that we need for every pixel at any resolution. Now, if you're interested in this flattening process, we have APIs on Android actually to do that for you. So if you use our Kotlin extensions, when you create a path, you can create the flatten method. It's an extension function. You can pass the flatness that you want to have, and we'll return a list of lines, and you can just inspect those lines. And interestingly enough, this process is not just for rendering, right? Let's say you want to move something along a path, or you want to compute the length of a path. Well, that's how you can do it, right? You can flatten the path with whatever flatness you want. Then you will get a bunch of lines, and animating or moving something along a line is very trivial, right? Much easier than trying to solve the cubic and the quadratic equations of the path. So this is a method that can prove useful. All right, last thing I want to show you is how we fill a path. So I showed you how we can draw the contour of a path, but not how we fill the inside. So here's an example where I drew a circle and I want a star cut out. So there are two types of fill modes for a path. There's non-zero and even odd. And you may have seen those values inside your drawing program like Sketch or Figma, or you've seen it in our APIs. So I'm going to show you how they work and what difference they make. So first, we're going to look at the even odd. So for every row of pixel, we're going to create a counter that starts at 0, and then we're going to walk through the pixels from left to right. As soon as we find an intersection, we're going to increase the counter by 1. So now the counter is odd, so we know we are inside the path, so we're going to start filling the path. Then we find another intersection, we're going to increase the counter again. Now it's 2 and it's even, so that means we're outside of the path, so that's a hole. We found another intersection, we increment, it's odd, we're inside, and so on. And now when you repeat that process for every row of pixel, you get the expected result. The other rule, called non-zero, works a little bit differently. It takes into account what's called the winding of a path. So the winding is just the order in which you've defined the points, right? Like here, the next point is to the right and down, so the winding is clockwise. If the next point was to the left, the winding would be counterclockwise. So here I drew those two paths, and they're both clockwise. So if we use the non-zero rule, we're going to start our counter. We're going to run into the first intersection. And here, we're going to increment the counter if the path is going up, so clockwise, or we're going to decrement the counter if the path is going down or counterclockwise. So here, it's clockwise, so we're going to increase the counter. It's 1, that means we're inside the path, non-zero, that's the rule. Another intersection, it's clockwise, so it goes up. So we're going to increment the counter, it's 2, it's still not 0, so we're still inside the path. Next one goes down, so now it's 1, but still non-zero, so we're still inside the path. And if we do that for every row, we're going to end up with a filled circle, which is not what we wanted. So the way to fix this particular path is to change the winding of one of the two objects. So hopefully the design tool that you use lets you do that. Or you can just change the order of the points yourself. And if you run the algorithm yourself, I'll let you do it if you're interested, you're going to end up with the same result as before. Very last thing, stroking. You can set a stroke on a path. Stroking is interesting because I said earlier that we try to our algorithms. It's a perfect example of that. So we're going to take our path. So here it's a circle. And then we're going to extrude the path. We're going to expand it. And that's going to give us 2 new paths, one on the outside, one on the inside. And then we can just fill that. So we just created a new path. And internally inside the rendering engine, that's exactly what's happening. We create a new path for you, and then we just fill it because we know how to fill a path. So there's nothing like magical about a stroke. It's more of a convenience, right? You could draw that object yourself instead. All right, so that's all for today. Like I said, we hope to have like more presentations like this in the future that will go beyond like the basics. So we want to talk about like the GPU and blending, how it works, clipping, anti-aliasing, gradients, 3D rendering, and all that stuff. And if there are particular topics you'd like to see covered, like please let me know or let Chet know, and we'll be happy to do that in the future. And hopefully we have 10 minutes left for Q&A.
Okay, thank you very much, Romain. That was a lot of very interesting things. So let me check if there's any questions coming in from the stream. It doesn't look like it. So we'll start with my questions because I do have questions. So I think the first one I want to ask is, when you were talking about the color spaces. So you were talking about Srgb, you were talking about Adobe Photo, you were Adobe Rgb, Profoto Rgb. Is there a specific reason, considering that we've seen in the graph that Srgb is the smallest one, the one that can represent the least amount of colors? Why don't we always use the one with the biggest supported?
Yeah, that's a really, really good question. There are 2 reasons for that. One is there is so much information we can encode over 8 bits. And Srgb happens to have been designed so that we know we can encode pretty much all the colors we can perceive within that triangle in 8-bit. So if you take a larger color space, you won't be able to get all the information over 8 bits, so you might get bending. The other reason is even simpler, is that most of our displays are not capable of showing more. And actually, until fairly recently, even laptops to display like full sRGB. And when I say recently, I mean like 10, 15 years ago. But the best displays nowadays that you can find like can display Adobe RGB or another one called P3, which is almost the same as Adobe RGB. But we don't really have displays that can display more than that. I believe there are some out there, but they cost like dozens of thousands of dollars and they're water cooled and stuff like that.
Got it. And so it's a quantization problem on the technical side and also a technology issue on the other side, on like a physical technology.
But what's interesting, right, is that you might want to use a larger color space as a working space. So for instance, if you use Lightroom to process your photos, it uses Profoto Rgb. That way, when you move your sliders, you're not going to lose any information, right? It's only when you save the final image, the color information you have, like shrink it down to, let's say, sRGB. But that way, if you ever go back, you haven't lost any information. You kept all the data. It also works, it uses like 16-bit per channel instead of 8 and so on. So those are still useful as intermediates. That's how the movie industry works. Even video game engines do this kind of stuff.
And when it comes to color spaces and image formats, are all image formats supporting all color spaces? Is there like limitations? Which one can support which?
Yeah, that's a good question. It depends on the format. Most modern formats, like starting with JPEG, like JPEG, PNG, Webp, all those, you can specify the color space inside. But GIF, for instance, has absolutely no concept of color space, at least that I know of. So you assume that the colors inside that are sRGB, but they might not be. So who knows?
It's likely, but
and usually that's the answer. Like, if we don't know what the color space is, we assume it's RGB because that's the only assumption we can make because this is so like common.
Okay, so I'm gonna jump to the next. I'm just going in order because as you were going through it, I just took notes because, as you know, I love this stuff. So when we're talking about text, so the next big chapter was text, and there was the example of creating the glyph atlas, so this big texture where you write all the letters, but that's a bitmap, right? And text, as you said, the fonts are vectors. So does Android keep different atlases for different fonts and different sizes?
Yeah, so I'm not sure how it works nowadays with Skia, but I assume it's something similar. But when I wrote it in libUI with chat, actually I have an article on Medium that explains that a little bit. But we actually throw like all the different font sizes in the same atlas. What we do, however, is that we have multiple atlases, right? Like because it's a balance between using too much memory and being able to show you all the glyphs that you need to see. So we have like different sizes of atlas, and then when we put them in one specific atlas. So there's a lot of strategies. Emojis go into their own because they're in color, and the other fonts are effectively black and white. Yeah, so it depends.
And when it comes to scaling things, so just jumping to the next topic. When it comes to scaling, you've shown the difference between nearest neighbor / sampling and bilinear. And you also mentioned that if you put bitmaps in the drawable bucket, Android assumes, because I guess of backwards compatibility, that that's the MDPI bucket.
Yeah.
So when you put something in the wrong bucket for the device that you're in, and Android tries to compensate for it, what kind of scaling does it do?
Yeah, so it uses bilinear filtering. It's the only one we expose. Skia now has other filtering methods that are better, for some definition of better. And I believe we will, or at least we've been talking about exposing them in the API. And there's one more that we have actually that's used for rendering. On a bitmap, you can, on a bitmap drawable, you can enable mip mapping. So that's a different topic, but basically mip mapping is you build multiple versions of the image, and then when you draw it on screen, you pick the one that's closest to the size you need. It helps us retain more information. But basically, bilinear filtering is what we use by.
So, well, bitmaps are somewhat conceptually similar to having different versions of the same image in different resolution buckets, right? Density buckets, sorry, in resources, correct?
Yeah. Yeah,
Okay.
because when you think about it, let's say you have a bitmap and you want to draw it at a size that's like 8 times smaller. If you use purely bitmap bilinear filtering, we're gonna miss a lot of information. With mip mapping, what we do is we divide the image by 2 multiple times. So at every level, we keep as much information as possible. So it's a better way to get sharper results, get nicer results.
Got it. You keep mentioning Skia. Maybe it's worth explaining what that is.
Yeah, so that's a bit complicated. So Skia is a 2D rendering library. It's used in Chrome and other systems as well. It came from Android actually, and it's what's behind Canvas. Then in Android 3.0, we wrote this library called BPUE that's basically Canvas on the GPU. So we're still using Skia to do CPU rendering, and then we're using this other library to do GPU rendering. And then in P, Skia over the years gained GPU capability, so we kind of threw away libGUI and we went back to using Skia. So it's our 2D renderer effectively.
Got it. Thank you. And if I'm not mistaken, there's also different capabilities that are supported in different Android versions when it comes to hardware acceleration because of the change of the engine, but also of the different things that over time the team has added, right?
Yeah, it was mostly, I didn't have the time to do like the whole thing at in one go, so we picked the most useful methods and then we kept adding features. But now, like I think everything should work on the GPU.
And when it comes to vectors, so you mentioned that like the way we draw vectors is we take a complex path, we subdivide it in simpler arcs that we are able to draw simply, and then we use the different winding modes, different fill modes to decide what is the inside of the curve itself. In terms of performance, is that something that happens on the GPU? Is that something that happens on the CPU?
Right. So that's the technique as described is how you do it on the CPU. For the GPU, the problem is that GPUs don't like to work the way I described. So there are other techniques. In libUI, for instance, the way it worked, and I think Skia still does that quite a bit. We render the path on the CPU as a mask, so you can think of it as a grayscale texture, and then we use that texture on the GPU to like mask off the paths that are not the path. There are ways to draw a path on the GPU, but it's very different. It's very different. And it's expensive.
Expect that since you're drawing the mask, the stencil on the CPU, the complexity of the curve might impact the time it takes to draw that. But once you've done it, it can be used multiple times without extra work.
Yeah, exactly. Yeah, so as long as you don't change the path, it's just going to become drawing a bitmap. So that GPUs are really good at that.
I think I'm out of questions.
All right, sounds good. And I'm out of time. I need to go to a meeting, unfortunately. But yeah, thanks for having me. It's always fun to talk about graphics. Hopefully that was useful and helpful to folks.
Thank you very much, and we're looking forward to the next parts of your series. Thank you again.
Yeah, me too. Thanks.
Bye-bye. And we will see you all at the next session with Android Heroes Live. And hopefully maybe we'll have Romain back for the next parts in the series, who knows. Thank you very much for being with us today. I hope you enjoyed this, and see you soon. Bye bye.